Hi, my name is Alastair Firth. I'm an SRE in Berlin for Camunda. Today we'll talk about deploying the ingress-nginx controller using Helm. Who are you? Well, hopefully you're figuring out how to deploy ingress controllers on Kubernetes, or you already have and want to see how other people are doing it. Just a heads up, there's a lot of code in this deck, so if you're on a bad connection and it's blurry, you might want to get slides from Sked or GitHub and follow along. So first, what you want. Traffic comes into a TCP load balancer, then goes to some highly available nginx reverse proxies, which terminate TLS, then hits your backend. Okay, I said we're going to do it on the Rails. If you pull up the docs for deploying the controller, you can just copy-paste these lines. Helm install, and then the name of your release, and then the chart name. So this part is pretty easy. Yeah, anybody who started here knows it's a bit more complicated than that. I guess that's why you're at my talk, so I hope I can help. Our use case is lots of single-tenant backends with their own URLs. Some use GRPC and some use HTTP 1.1. We have multiple Kubernetes clusters in multiple regions. The solution should allow layer 4 routing to a specific cluster, like we did in 1998. We also want to be cloud provider agnostic. Frankly, not many providers support single, let alone multi-region gRPC layer 7 load balancing anyway. I think there's only one you can buy. Some similar use cases include customer-created CNAMEs pointing to a unique URL hosted by you, like many web hosting providers, or PR-based environments for CI/CD, or perhaps Kubernetes platform as a service for your company so devs can deploy new services autonomously. Back to the Rails. Obviously a disclaimer, I'm not endorsing these on behalf of anyone, just saying they're in common use and to my knowledge the most widely used open source solution. They also have maintained Helm charts. That's good for us. Shout out to all the maintainers. Thank you 1,000 times over. ExternalDNS is a controller which watches ingresses and makes, well, external DNS records. Cert-manager is a controller which watches its own CRDs and creates TLS certificates as Kubernetes secrets. These secrets can be referenced by ingresses. Optionally, it can also watch ingresses and solve HTTP 01 ACME challenges, which it puts in the already referenced secret. Prometheus operator is a controller which watches its own CRDs. It deploys Prometheus, Alert Manager, and Grafana, as well as allowing you to store dashboards and alerting rules in their own config maps, which the app developers can own. OS2 proxy is a separate service which can authenticate the user, optionally requiring some scopes like a particular email domain or GitHub team membership. Nginx can route incoming requests there and only pass them onto your backend if they're successful. Before we dive in, I think there are three main pain points when you're working on this. Firstly, deploying everything, and in particular managing secrets. For example, you might have multiple clusters in multiple regions for production, but different URLs and credentials for test environments. Keeping everything in sync and continuously delivered without copy-pasting everything can be tough. The tooling is still stabilizing, and I don't think anyone is convinced that we found the way to template this stuff. Secondly, tracking upstream improvements. Although the rate of change in this ecosystem is much slower than it was a few years ago, it's still much higher than most enterprise software of the past, and you'll be out to dry by yourself if you're more than about 12 months behind. CVEs get patched and released very quickly, and one of the major benefits of this stack is being able to quickly and easily upgrade small chunks of your infrastructure at a time. Lastly, every service we've talked about comes up with a minimal feature set. In a production scenario, you need to set a lot of configuration. Although more and more of the recommended config can be found in the chart repos, you'll often be piecing together bits from blog posts and GitHub issues. I want to spend most of our time on the last one, but first I'll explain how we solved the first two, which aren't unique to this space at all. Okay, so the solution we came up with for the first 2 points is pretty straightforward. Basically, we use SOPs to encrypt all the secrets and add them to customized overlays. We call Helm template on each chart with our standard values and add this output to a customized base. Then we make overlays for different clusters and environments to set things like the domains and inject secrets like DNS provider access tokens. Then we call customized build for each cluster and pipe it to kubectl apply. It's pretty easy. Helm template, kubectl apply. Of course it's not easy. That's why you're here. It's still 100 times easier than it was a few years ago though. The hardest part is tweaking each component for different clusters. The approach we take means that we have plain Kubernetes manifests, one per cluster, in Git. The main disadvantage is that deployment pipelines or operators need to take care of things the Helm hooks usually do, like installing CRDs and waiting for the validating webhooks to come up. This might be an issue for you if you deploy a lot of clusters. In practice for us, since it's idempotent, the first bootstrap deploy fails, and then we rerun it and it works. It plays nicely with CD systems like Argo and Spinnaker, and also allows an engineer to run kubectl diff. Our app developers typically write controllers or customized manifests and not Helm charts, so this keeps the pipeline similar. Manifest diffs are valuable for seeing what will actually change when you update a Helm chart. You could get the same with multiple helm-values files all stacked up and then calling helm dry run, but it's not visible in the PR. However, by far the most valuable part when we set out on this path was that we didn't have to fork Helm charts to expose a value. However, at this point, most charts support options like extra args or extra envs, so that might not be such an issue for you. If you feel like you've already solved deploying charts, or this doesn't apply to you because you have only one cluster, just let your eyes glaze over for 5 minutes and we'll get back to the fun bits. Okay, if we were live, I could probably see some people cringe that I've got screenshots of code in my presentation. Backstory is that at my first KubeCon, I went and I heard about all these cool things each piece of software could do, and then I spent the next year figuring out how to do them. So the format of this presentation is basically me walking you through our production code and calling out line numbers and what they do. We're going to smash through all 5 Helm charts and the deployment pipelines in 35 minutes, so buckle up. So back to how we solve the deployment and secrets problem and follow upstream changes. First part is a makefile for each chart. It looks a lot like what you do by hand to install a Helm chart, except at line 22 we call Helm template instead of Helm install, which produces manifests on standard out instead of installing them in the cluster. And then at line 28, add them all to generated/customization.yaml. One thing is this is Helm 2, Helm 3 changed the args a bit. We use basically the same makefile for all charts, although line 30 changes a bit if they have subcharts. Don't stress if you think this is crazy, it's just context for the files we have moving forward and should be adaptable to whatever process you have. If you don't have one, this is a pretty complete solution that works for all of these use cases. So here's the base customization.yaml on the top left, and you can see the directory structure of the base on the right. The entire untarred chart is in generated charts, so if you need to fork the chart, you can just commit your fork here. The base level customization here contains a namespace and a reference to the generated customization.yaml, which we made with makeGenerate. It could contain any other resources that aren't in the Helm chart, but are the same on all clusters. Now that we have this base, we can include it in customized overlays for different clusters and environments. In the overlay, we can layer customized manifests on top of each other and patch them in a variety of ways, or combine multiple resources. Finally, calling customized build on the overlay creates YAML that you can pipe to kubectl apply. On the right, we've got the directory structure of our overlay. This is specific to one cluster. So in the resources section of our overlay customization.yaml, we've got a reference to the base, which we just looked at, and another customization embedded here, which contains, in this case, the alert manager secret, which is 99% config for alert routing and 1% top secret webhooks. This is the only secret the Prometheus operator needs, and is also a nice segue into how we handle secrets. Okay, so this is the alert manager secret customization, which is referenced by that overlay. Notice hashing is off. This particular secret name is hard-coded by the operator. However, the operator watches its changes, so changes are picked up. Generally, you can reference the secrets directly from the overlay and leave the name suffix hash option on, which will make everything that mounted the secret or config map restart. Kustomize supports adding secrets in a number of different ways. This particular one is going to pick up everything in the file as a complete Kubernetes secret and give it a long and complicated name. Here you can see a portion of the alert manager secret it references. Note that only the sensitive Slack API URL on line 3 is encrypted. SOP supports specifying a particular suffix to encrypt. One cool thing about this is that although the manifests won't be deployable, they are valid YAML even when the secrets are encrypted. That means Kustomize builds them just fine, and you can see the overall changes in PRs if you commit the manifest for each cluster without exposing any secrets. SOPs uses a .sops.yaml file similar to a .getignore file to specify how you encrypt and decrypt secrets. So the top file on line 4 and 6 uses 2 different KMS keys depending on the encrypted file location. That's important if you want to control access to the secrets for different clusters. Finally, we have another makefile to decrypt all the secrets during deployment just before we apply the manifests to the clusters. This makefile is wrapped up into a Docker file, which I'm showing you here because I hate hand-wavy vapor code in presentations. Slides are online and hopefully they'll be in GitHub. And then finally, our deploy pipelines just call sops decrypt with that Docker image, and then Kustomize build pipe kubectl apply. All of this looks pretty much the same for all the chart-based repositories. There are some alternatives for secret management. which has historically been considered an insecure part of Kubernetes installations. etcd is much tighter than it used to be, supporting TLS and encryption at rest by default, and if you're running single-tenant clusters, it's up to you to decide if these alternatives provide any real benefit. The main leak vector for SOPs is in the deploy pipeline logs or inadvertent commits of plaintext. Vault and sealed secrets both wait until the secret is in the cluster to decrypt it, and Vault doesn't put it in etcd at all. That can be pretty hard to inject into some of the chart deployed stuff, but worst case you can decrypt it in your pipeline. Most cloud providers also have a secret management solution now, so your mileage may vary. Okay, so to summarize, we've solved all the painful bits. We generate plain Kubernetes manifests for each target cluster, which are safe to commit with Helm template, SOPs, and customize, and we deploy them with kubectl apply or whatever magic goo you like. To fetch upstream changes, we just run our makefile to pick up chart changes and check the diffs of the manifests, either in Git or with kubectl diff. If you think this is ridiculous, that's okay. When I wrote this, Tildeless Helm was cutting edge. It's just background, but I hope it helps some of you. Now, onto the fun bits. Using cloud-native software to do stuff that used to be hard, expensive, or both, just by setting some config options. How exciting is that? Some of you kids probably never even bought an SSL certificate. Lucky you. This bit's going to be a whirlwind of code. I'm not trying to impart any profound wisdom, just show you useful options and how to set them. First, ExternalDNS and Cert-manager, then a basic Prometheus operator deployment, and an OS2 proxy to put in front of it, then finally the ingress controller itself. First, we need a quick overview of an example ingress. This is a service we have called accounts. Ingress v1 is a bit of a weird resource because there are so many implementations of controllers, so a lot of stuff is happening in the annotations. Controllers like ingress-nginx, external-dns, and cert-manager will use a combination of the annotations and spec to decide what, if anything, to do when they see an ingress resource. There are three main sections here. At 5, the annotations, including the external DNS directives, the class to ensure only one controller tries to serve it, forced HTTPS, and an example of rate limiting. At 13, the routing to the backend in spec.rules, and at 19, the TLS configuration in spec.tls. You might notice we're missing the secret in the TLS section. That's because we're using a wildcard as the default cert. More on that later, but for now, let's jump right into line 6 and 7. External DNS is the first controller we'll look at. It's going to create some DNS records on Cloudflare for us when it sees this ingress. Here you see it working. It's created an A record pointing to our load balancer and a text that this particular external DNS owns it. If the ingress is deleted, it will delete both. Another copy of external DNS won't override it unless the TXT record matches what it's looking for. Just a little side note that many providers limit the total number of records you have. Cloudflare Pro is about 2,500, so don't go crazy. Okay, so here are the helm values we'll use as a base for that external DNS targeting Cloudflare. Firstly, on line 2, the default is to watch services as well. We limit to ingresses for reasons I frankly don't remember. On lines 11 and 14, we set the provider-specific stuff, and we blank out the API key so it's not set. We'll set that later in a customized patch. 17 and 18, logging is cheap, and you really want to know what's going on if this screws up, so turn it up. We use JSON logging everywhere we can for easy searching and metrics making. Line 19, we set the policy to sync as opposed to just upsert. This means we'll actually delete unneeded records if we own them according to the text record. We'll set that owner in a patch too. 21 to 37, we set security stuff and resources. 38, we enable the metrics endpoint and also deploy a service monitor custom resource which will be picked up by the Prometheus operator. It's easy. I think you'll agree it really is easy this time. No memes. This is an overlay patch for the external DNS deployment, which we apply with customized for a particular cluster. We're just overriding some envars. Firstly, at 12, we set the authentication info. For Cloudflare, this is required, but if you're using a cloud provider's DNS, you can also just let it pick up the default credentials. For GKE, you need to grant the nodes the scope to do that. It's a similar process for other providers. Most DNS providers are supported. Secondly, on line 23, we need to set an owner ID. This is a key which should be unique per external DNS installation and will be used in that text record. At 25, we set a domain filter which should correspond to the zones you have creds for. Multiple domains can be provided, but, and this is a recurring theme, domains are probably a good system boundary and you might want to consider your splits. We create the secret referenced on lines 14 and 19 pretty much the same way we made the alert manager one, and for Cloudflare it's used by Cert-manager too, so let's jump over there. In our setup, Cert-manager's main job is to make sure we have a valid TLS certificate for each ingress. Just like the old kube Lego, you can configure it to solve an HTTP 01 ACME challenge with Let's Encrypt for each ingress and set a secret name. However, you can just give nginx a wildcard for all your ingresses. Even if you have multiple domains to serve, you can have a single certificate, assuming you solve all the challenges. Note at line 8, we set the ingress class. Each controller can be configured to watch a specific class, so you can run multiple ingress nginx's or even mix and match with other ingress controllers. Back to that magical certificate. There are 2 custom resources which you need to provide for Cert-manager to get this working. Firstly, a cluster issuer on the left tells it how to solve challenges. For wildcards, we need to use DNS-01, and we're using Cloudflare with the same credentials as external-dns. Everything here is required, but also pretty self-explanatory. On the right, we have a request for a specific certificate, which will be saved in the Cert-manager namespace as a secret called wildcard TLS. Because wildcards are only good 1 level deep, you need to provide any subdomains you want here. If you change the subdomains later, you'll get a scary expiry email for the old certificate 90 days later, so set a calendar reminder to ignore that email. Obviously, Cert-manager needs to be installed before you can create these custom resources, so let's dig in. For Cert-manager, Jetstack actually releases a manifest created using Helm template themselves, so we just pulled that. I think I had too much coffee when I upgraded us from 0.10 and I wrote this monstrosity. Sorry. Just use the Helm chart like all the other things, or download the manifest. As it says in the comments, hopefully customize 2167, which is now merged, allows you to reference this in a customize. So skip right over this over-engineered mess. The point is that you need a customized base containing the default Cert-manager installation manifests. With the ability to pull HTTPS URLs from customize, hopefully by the time you're reading this, you can ignore the last slide and use a simple base customization. Anyway, once we have the static manifests, somehow or another, we patch them as usual, except there is nothing to patch because James is awesome and it's all just custom resources. Deploy the base manifests, the cluster issuer, and the appropriate wildcard cert, which are the 2 CRDs we just showed. Easy. Thanks, James. OS2 proxy is pretty straightforward way to secure your monitoring services, which supports 13 specific auth providers, plus all OIDC implementations like Okta and Dex. We've set it up to make sure people are in our GitHub org. This is the Grafana ingress, showing how the request is routed to the proxy first. Note that we use best HTTP host and include 2 XAuth headers in the request we pass to Grafana. This lets Grafana create a user internally if it doesn't already exist. The rest of this ingress looks like any other. Alternative is to use some sort of identity-aware proxy in front from a cloud provider or a SaaS. There are plenty of people making money deploying the next 3 slides. This is the helm-values file for OS2 proxy. Line 2, we ensure it doesn't try to make its own secrets. 4, we're setting up the ingress placeholders to patch later. 12, we configure some logging and make sure it actually passes the auth headers we need to send through to Grafana. 17 is the provider-specific config. And then continued on the right, on 26, we've got the resources, and on 36, an example of pod anti-affinity for 2 replicas. Since this is an internal-only service for us, it's a perfect candidate for preemptible nodes. All we need to patch for OS2 proxy are the domain names, but if you wanted to patch replicas or resources for a particular environment, you could do that here too. Again, these patches are applied by customize per environment or whatever Helm template made. Finally, we have the secret for the OS2 provider, which we add with customize. Here, we're using the end file format for customize to create the secret to access our GitHub OAuth app, and again disabling the suffix hashing, which unfortunately means we'd have to roll these pods if they don't fail probes when we roll a secret. In the middle is the plain text, and at the bottom is what it looks like committed. That's it for OS2 proxy. You don't actually need one per cluster. You can send requests to an OS2 proxy located in a different cluster using its DNS name, which ExternalDNS kindly created for you, and the request will be secured with TLS from your wildcard cert. I'll show you that in the monitoring section. You can also cache the responses if you like, using ingress annotations, but I won't go into that here. So, on to Prometheus operator. Frankly, this chart is amazing. Not only does it deploy the operator, it also deploys alerts and dashboards for common kube components. One thing that is completely different from a vanilla Prometheus setup is that you scrape services using a service monitor CRD rather than an annotation on your services. The service monitor uses a label selector to pick services, and then the operator updates the Prometheus config automatically. Service monitors, dashboards, and alerting rules can be deployed in any namespace, so your application developers can keep them right next to the code. This diagram is oversimplified, but if you've never seen metric scraping before, hopefully it gets the basics across. What does Prometheus have to do with ingress-nginx? Well, with a few lines of config, you get two amazing dashboards for the ingress-nginx repo. You've got nginx performance, latency, throughput, and error rates, and certificate validity. And they can be broken down by path, service, and controller class. There's a fair bit to set up here, and everyone is going to have different use cases. I'm just going to cover the highlights of our config, and you can find more at the GitHub link in the corner. One caveat is that this config is for version 6 of the chart, and it's on 9 now, so apologies for that. There's no huge changes though. I'll just go through the helm-values. Patches are applied the same way as other systems. Line 1 is a workaround to force Helm to generate resources for older kube versions in case the API has changed. I'm not sure what we're working around, but there you go. On 4, we're setting JSON logging. 5 and 6, retention time and size, slightly lower than our volume size, and then resources. On 15, we're also running multiple replicas with anti-affinity, which is especially easy to configure with this chart. 19 and 20 probably aren't needed anymore, but told the operator to look at CRDs regardless of their labels. 22, we give it a physical volume. 31, we configure session affinity so your values don't change as you browse if a replica has partial data. And finally, on 33, we have the ingress placeholder, which we patch as shown before. Alert Manager spec is here for completeness. This is in the same file. Not much going on besides configuring the ingress, logging, and storage. Most Helm charts have storage off by default, so they work for demos and CI, but you probably want persistence for production. Note at 54, we again tell it not to create a secret. We showed the Alert Manager secret, which contains the routing rules earlier in this presentation. Grafana is tricky. At line 74, we're setting a bunch of M variables for auth. These override the Grafana INI file, which is a pain to template. The end result is that anyone coming in through the ingress has an account and Explorer access. They can save dashboards, but these won't be synced. Instead, what we do is kube port forward to be an admin when we create dashboards, then export them to JSON through the Grafana UI and save them in Git. It's a bit of a pain, but it means the dashboards are in Git, which makes them easy to sync across stages. At 114 is the directive to the sidecar to look in all namespaces for dashboards. Finally, on the right, we make sure operator logs are also JSON. Back to dashboards. The cleanest way to fetch dashboards with the operator is by URL. This also keeps it in sync with upstream. Of course, you might want to fork it so that it doesn't break suddenly. This is a not very well documented feature of the sidecar, but it's awesome. You can also embed the dashboard completely as a config map. On line 7, you can see the label which the operator uses to decide what config maps to pick up and inject into Grafana. Similarly, there's a CRD for recording rules and alerts. That's enough about monitoring. On to nginx. Again, we're a bit behind the latest chart, so some of the things we've worked around might have been fixed upstream. Here's the helm values for our GRPC handling controller, and we'll go through the highlights. You can find a fully annotated values file in most of the helm charts, complete with the default values. All of these just overlay on that one. Line 2 to 4, we're configuring this as a deployment rather than daemon set because we'll make load balancers instead of just publishing the node IPs to DNS like in many tutorials. This controller will watch any ingress with the class annotation of GRPC. On 8, we publish the service, which is required for ExternalDNS to make A records with the correct IP. 11 is the magic juice for wildcard certificates. This is the only way I'm aware of to refer to a certificate in a different namespace with this controller. And this sets the TLS certificate for the default route and any other ingresses that don't set a secret name in the TLS section. Alternatives are to use something like kubed to sync the secrets across namespaces, or use HTTP/01 ACME certs. If you do use HTTP/01, beware of rate limits at Let's Encrypt. Of course, you can also have every application include their own certificate CRD. 14, we change the status code returned if the client is rate limited. By default, it's 503. Nobody likes alerts about bad clients. 15 to 19 are Stackdriver compatible JSON access logs. I've linked the gist so you don't have to dig through everything. Again, this is access logs. There's no way I'm aware of to get nginx error logs into JSON via config. 22 to 25 are global settings we use for GRPC. In particular, the HTTP2 max request setting is increased from 1000, which is important for long-lived connections, but may impact memory usage. 26 uses the x forwarded for header for rate limit and caching buckets, which is really important for HTTP traffic proxied through Cloudflare, otherwise you'll rate limit an edge. See, I saved you an incident. Same file. Next, on 27, we set up anti-affinity. Then on 44, memory and CPU. And from 52, a horizontal pod autoscaler from 3 to 6 replicas. Moving right along. Finally, at 64, we make sure this is exposed on a load balancer and the client's IP is preserved. And at 68, we enable metrics and deploy the included service monitor for the Prometheus operator to pick up. We don't have any patches for nginx, we just run the production setup on all clusters and rely on the autoscaler. However, you could conceivably want to patch the resource usage or even change some controller global settings in the config map. Most configuration options can be set in each individual ingress as an annotation, and the docs are pretty good about this. Worst case, you can even embed raw nginx config as an annotation. I promise some... Oh, no. Yeah, I promised some GRPC specific stuff. This is one tweak which will return... Okay, sorry about that. I had some technical issues. Anyway, yeah, this is one tweak which will return GRPC native error codes for GRPC's ingresses. This is just a section of the config which you could embed in your controller by putting it in the controller config map. I highly advise keeping your HTTP2 traffic separate from the HTTP1 traffic by deploying a second ingress controller. That also means an extra $30 in load balancers, but it's worth it in production, I think. The downside of replacing the error codes like this is that the monitoring is going to break, because the HTTP2 spec is that the HTTP1 status code is 200. Actually, I think the 204 here is non-compliant. Anyway, it's an option. Some of you might be wondering why we use nginx to proxy GRPC at all. Well, it's mature, fast, and fairly stable. You're unlikely to see a problem that you can't search for, and most operations engineers have used it before. There's lots of samples, and things like adding an auth proxy or rate limiting are well documented. For us, making this choice in mid-2019, it was a choice of running nginx for HTTP and a second, less mature controller, or getting nginx to play nicely with gRPC. What we have works pretty well for our use case. When we first started, we tried to integrate Linkerd2 to provide the request level load balancing and even more monitoring, but we ran into some nasty bugs. As far as I know, those have all been fixed over the last year, so our next initiative on this front is to reevaluate that and also survey the state of the other ingress controllers. Okay, that's it for this presentation. Quick recap, we looked at how you can deploy all of this to multiple clusters with different values for each cluster, using a combination of helm and customize, and secure your secrets with SOPs. We've now got automatic DNS records being created by ExternalDNS based on ingress annotations, wildcard certificates from Cert-manager accessible from all those namespaces, Prometheus operator scraping our ingress controllers and showing us metrics in Grafana for each individual ingress, authentication in front of those metrics with OAuth, and finally nginx with a basic gRPC setup and rate limits. I hope you've enjoyed the presentation. Again, slides should be on Sched and GitHub, along with some sample code. Please join me in the chat for any questions.